Hello everyone, welcome to this part of the presentation. I am Ali Arjomandi Nezhad, a PhD student at Imperial College London, working under the supervision of Professor Vikash Paul. At this part of the presentation, I'm going to talk about InnoCyPES Net Zero Benchmark System. This system is an open source system that you can download it from Zenodo if you are interested to work with that. At this presentation, first I'm going to talk about target capabilities of InnoCyPES Net Zero benchmark system. Then before I explain the system diagram, I will talk about hierarchical frequency control and effect of inertia and droop change. And then system diagram is introduced. It is followed by demonstration of the test system in Simulink. And then case studies will be studied. And an optional assignment will be also recommended to do, and the talk will be wrapped up by the conclusions. The aim of this test system is being used for a stability analysis, specifically for these items: fast interaction converter driven stability. The fastest control loop that we implemented was current controller. So PMW is not implemented in details. The average model is used for the inverter, but other parts of the control from current controller as the fastest and secondary frequency control as the slowest is implemented in detail in the Simulink environment. It can be used for synchronization stability studies, either transient stability or small signal stability, and also for frequency stability and voltage stability. As you know, the load of the power system always changes. Therefore, the frequency controller, which has 3 layers, is responsible to make the load dispatch and keep the frequency of the grid in acceptable range. The fastest layer of frequency control is primary PF controller, which doesn't need any communication, and it acts based on the local measurement and droop control law. Then there is secondary frequency control, which is a bit slower because it needs communication of tie line power, and it tries to bring the frequency back to the nominal frequency subjected to the acceptable change of the active power of tie lines. Then there is tertiary PF controller, which aims at optimizing the cost of optimal set points. And this one, tertiary PF control, is not implemented in this test system, but primary and secondary PF control is implemented. You can see that in a power system, the fastest element in the frequency control is inertia. It activates in a very fast time, and it prohibits the fast change of the frequency. Then there is primary control, which changes the power and frequency based on droop law. And then it's secondary control, which tries to bring the frequency back to the nominal frequency as much as possible. If more droop is provided, then the steady state point of the primary frequency control would be more close to the nominal frequency. However, if more inertia is provided, the rate of change of frequency would be less. Therefore, both droop and inertia are some essential elements for the grid. This is the system diagram of the InnoCyPES Net Zero test system. It's modified IEEE 14 bus system. Synchronous generators and conventional power plants has been replaced with grid forming and grid following resources. Different colors in this diagram represents different voltage levels. The grid is divided into 4 areas. Area 1 has 1 grid forming and 2 grid following, and it is responsible for the most of the generation of the grid. Area 2 has 1 grid forming and 1 grid following, and 1 very big load at bus 2. Therefore, area 2 is the biggest consumer in the grid, and most of the power follows from area 1 to area 2. Then there is area 3, which has 1 grid following resource, and area 4, which doesn't have any grid forming or grid following resource, and it's totally passive. And this test system can be downloaded from Zenodo in open source. At this part of the talk, I'm gonna show the Simulink file of the net zero system and explain how to work with that. Can you see the MATLAB?
Yeah, we can see you. Go ahead. Yeah.
First, when you download the deliverable D3.2 from Zenodo, you can put it in a folder as the directory of MATLAB. Then initialization file should be run in order to load data from Excel files and bring it to the workspace. After that, you can load the Simulink file and run the simulation. Different colors in this Simulink file represents different types of element. Blue elements are grid forming elements. Orange elements are grid following elements. Green elements are communication and computation elements. For example, here at this part, you can see PMUs measure the magnitude, angle, and frequency, and it will be sent to the monitoring part here. Now let's talk in more details about the grid forming and grid following blocks at this deliverable. The grid forming component at this deliverable contains several layers of control which has different time scales. The outermost layer is secondary control, which change the reference point of the power of the primary controller. The primary controller is virtual inertia and droop control, which emulates the inertia, and it provides the frequency and angle of the primary angle reference for the system. Then there is voltage controller. Voltage controller generates the reference magnitude of the voltage based on the reactive power voltage droop law. Here you can see. Yes, you can see that it generates the reference for the magnitude of the voltage. The reference for the magnitude of the voltage and reference for the angle is given to the voltage controller. Voltage controller in this case is the decoupled voltage controller with feed-forward term. Feed-forward terms coefficients in this deliverable is 1, but a lot of researchers in literature have proposed that this feed-forward term can be a bit less than 1 to make it robust to change of the grid strength. but we have used one. If someone is interested, they can change this coefficient for some other value and check the robustness. The voltage controller produces the reference for the current, and this reference is saturated if it goes beyond the limitation. This is something that happens in transient stability studies. When there is a big disturbance, it easily goes to the current saturation mode. But for a small signal studies, you don't need to consider the current saturation. And then finally, there is current loop as the innermost layer. It is also decoupled and has feed-forward term with the magnitude of 1, but a lot of research has proposed to choose another value less than 1 to make it robust to the change of the grid strength. You can try that and see how it affects, but this one at this deliverable, it's this coefficient is 1. Another element is grid following converter. Grid following converter reads the frequency and voltage of the grid through PLL. So the voltage is given to the PLL, and based on the Q element of the voltage, it produces the frequency and angle for the inner controller. And it has also current controller as the fastest layer of the controller, which is the same as the current controller that we saw a few moments ago. We have performed a few case studies that I'm going to talk about, two of them at this presentation. One of them is a change of load. If the load change, then the frequency drops because of the change of load, and then the frequency comes back to the nominal frequency because based on the hierarchical frequency control. And also the change of the load will be dispatched between two grid forming elements. Another scenario which has been studied is the scenario of three-phase fault at bus 6 for 50 milliseconds. We have observed that if a fault happens, the frequency of grid forming 1 and grid forming 2 increases. And this is what we expected because they are working based on the group, based on the second order swing equation. When there is a fault, they cannot send power to the grid as much as there is the set point. Therefore, their frequency increases. However, we can see that grid following 3 and grid following 6 cannot estimate the frequency of the grid well. Because when grid formings make the frequency of the grid followings should follow these frequency made by the grid formings, but grid followings, one of them, which is grid following 3, estimates the frequency much more than the frequency which is generated by the grid formings, and another one, which is grid following 6, estimates under frequency. This is something um, unwanted, undesired, because now grid following 3 and grid following 6 has the frequency difference of about 0.75 hertz. So the current that these two generators are generating have this much frequency difference, which is unwanted. You know what is the reason? Because grid following do not read the frequency directly. They read the frequency based on the voltage. And the voltage during the fault is disturbed. And the reactive power flow is also disturbed. So now we can see that when there is grid following, there is high link between reactive power and voltage, and frequency, and synchronization. This is something that in traditional grids did not happen, because in traditional grids there was a strong link between power and frequency. Now, because of the PLL, since PLL is reading the frequency based on voltage, voltage has a predominant role in frequency control and synchronization. And also another thing which happens is that 0.9 hertz frequency difference between grid forming 2 and grid following 6 a few moments after the fault. And this is not also desired. One question that I want to ask you, audiences, either online audiences or audiences in room, is that now we can see that there are huge frequency differences between elements. From the point of view of required tools for the simulations, what can we conclude? Feel free to unmute your microphone and talk about it. Do you have any opinion that this observation tells us something about what we need for simulation tool? Anyone from the audiences? So I'll tell now. This observation, this big frequency difference, tells us that we need EMT simulation, because RMS simulation or phasor domain simulation is based on the base frequency. At that simulation, it is assumed that the frequency is not deviated much from the nominal frequency. However, we can see now there is high frequency differences between elements. So we need EMT simulation for a more precise result. There is an optional assignment. You can download the test system by scanning this QR code. Then increase the reference power of grid forming 1 by 1% for 2 seconds, and then return it back to normal value and record frequency change for this scenario. Then increase virtual inertia of this grid forming by 10% and repeat these two stages and record the result for the frequency. Compare these two and see what happens. This is the optional assignment for this part of the talk. So at this talk, we saw that the Simulink file of the test system is introduced and demonstrated. We saw two scenarios, load change and three-phase fault, and the necessity of electromagnetic transient simulation, in addition to traditional methods and tools, have also been observed. Thanks for your attention. Now